Okay, so now we're going to start with chapter 4, and as you can see on your screen, chapter 4 deals with the topic of elements, atoms, and ions. So this is basically an introduction to these different concepts. So let's talk about elements firstly. What are elements? If I'm not mistaken, we dealt with elements in either chapter 2 or chapter 3. The definition of an element, if you remember, it is basically a substance, a fundamental or elementary substance that cannot be broken down into simpler substances by chemical means. And we all know about the periodic table, which is the list of known elements that we have obtained so far or synthesized so far. And these number about more than 100. All right. Now, each element has associated with it a number. And that number is known as the atomic number, beginning with hydrogen, which has the atomic number of 1. And then as you go from one element to the next in the periodic table, you'll notice that that number increases. Later on, we're going to discuss the significance of that number, what that number actually means. Now, most substances can be decomposed into two or more simpler substances, and these substances are known as compounds. For example, a simple example would be water. Water can be decomposed by electrolysis into hydrogen and oxygen. And table salt, which is sodium chloride, can be itself decomposed, again by electrolysis, into sodium and chlorine, right? But those are compounds and not elements, because as we said before, an element cannot be decomposed into simpler substances by chemical means. Now, how are the elements distributed in nature? Well, as stated here, elements are not equally distributed. For example, if you look at the human body, the most abundant element in the human body is oxygen at about 65%. Oxygen is also the most abundant element in the crust of the earth. But in the universe, the most abundant element is hydrogen, while the second most abundant element is helium. And as you can see, there's a big disparity between the two in terms of their percentages. So this is just basically showing you, using a pie chart in each case, the relative abundances of the different elements in the universe or in galaxies, on Earth, on the Earth's crust, in seawater and air. And here you see the pie chart for human bodies. And as stated earlier, oxygen is the most abundant element in both the human body and in the Earth's crust. But in the universe, the most abundant element is hydrogen. All right? So that gives you an idea as to how much of each element is present in these different areas, in these different regions. Now, let's look at how the elements are named, right? There are different sources for the name of elements, right? In some cases, the elements are named based on their color. For example, iodine, which comes from a Greek word meaning violet. In other cases, the element name is derived from a property of a compound containing that element. So fluorine comes from a Latin word which means to flow, and it says here that fluorine, this fluorine containing ore called fluorspar, has low melting. That is essentially where the name comes from. And here's another example of the name derived from color, bismuth, which comes from a German word which means white mass. And also you can have the element name based on the location of, in this case, the location of the birthplace of a German chemist, right? Germanium is that element, which is named after the country of German. And then lastly, we have in some cases where the name of the element is based on the name of some famous scientist. So for example, Einsteinium is of course named after the famous physicist Albert Einstein. Okay, in chemistry we use shorthand symbols to represent elements instead of writing out their names. So in some cases a symbol can stand for the element itself. In other cases it can stand for one atom of the element, especially when we're looking at the symbols used in equations. In other cases, it can represent a particular quantity of the element. The rule governing the symbols of the elements are, it must be a symbol which contains or consists of one uppercase letter or two letters. One is uppercase and the other one is lowercase if it's two letters. So if one letter is used, it is uppercase or capitalized. such as hydrogen, such as carbon, right? But if you have two letters, only the first letter is capitalized. The second letter is lowercase, such as neon, such as barium, and yeah, that's it. Okay, so basically those are the rules when it comes to naming um, elements. Now, this here is a list of the most common elements that you will encounter. And what you're going to see is that in some cases, in fact, in most cases, most symbols start with the same letter as the element. So that can be seen in these two cases, aluminum and iodine. The symbol for aluminum is Al. The symbol for iodine is I. The symbol for hydrogen is H. The symbol for helium is He, and so on. So in some cases, it's obvious, kind of, the relationship between the symbol and the name. In other cases, there appears to be no connection between the symbol and the name of the element in English. And the main reason for that is that if you look at the history of naming these particular elements, you'll see that these elements had some early names based on different languages. I think Latin is the main language that was used to name these elements earlier. So, for example, the element now known as antimony, its symbol is SB. Obviously, there's no relationship, obviously, between these two. But if you look at the first name or the earlier name of that element, it was called stibium, right? In the case of copper, its symbol is Cu, its former name is cuprum, and so on and so forth. Tungsten, its symbol is W, and that's because its previous name is wolfram. All right, so that's how some of these elements end up with symbols that have no bearing, no relationship to their names in English. Okay, now there are some different ways of categorizing elements. We can categorize them according to their groups and so on, but one category or a type of categorization that we're going to use in this discussion is the categorization of elements into metals, nonmetals, and metalloids. So let's talk about metals. What do we mean by metals? Well, the metals can be identified by their physical properties. So metals, pretty much all of them are solids at room temperature with one noted exception, and that exception is mercury. At room temperature, mercury is a liquid. Another property that metals tend to display is that they have high luster, which basically means that they are shiny, right? Another property that metals display is that they are very good conductors of heat and electricity, without exception. And then you have here another property which says that metals are malleable, which basically means that they can be rolled or hammered into sheets, all right? Metals are also ductile, which means that they can be drawn into wires. And most metals have a high melting point, all right? And finally, here we have metals also having high densities. So those are the properties displayed by metals. And some examples of metals include gold, iron, lead, and those are the examples that we have. Now, in terms of the chemical properties of metals, right? One is that they have very little tendency to combine with each other to form compounds. In fact, to be perfectly honest, I can't think of any situation where two metals react with each other to form a compound. However, they do tend to combine with nonmetals to form ionic compounds. So you'll find metals reacting with elements such as sulfur, chlorine, and oxygen, all right? So that's basically how metals tend to behave. And in fact, in nature, a lot of the more reactive metals you'll find in the form where they're combined with other non-metallic elements, all right? Some other chemical properties of metals. There are some metals that are not very reactive, such as copper, silver, and gold. So therefore, when they're found in nature, they tend to be found uncombined with other elements. Metals can mix with each other to form alloys. In fact, the term alloys basically means mixture of metals. So for example, brass is a mixture of copper and zinc, and bronze is a mixture of copper and tin. All right. This is not really an alloy because carbon is not a metal, but steel is actually a mixture of carbon and iron. Okay, so let's talk about the second category of elements, nonmetals. They tend to be basically the opposites of metals in terms of their properties. They tend to lack luster. In other words, they tend to be dull. They have very relatively low melting points, generally speaking. And by the way, there are some exceptions to these properties. So what we're saying or talking about here are general properties. They tend to have low densities. They tend to be poor conductors of heat and electricity. And at room temperature, there are only these elements, these 5 elements that are solids: carbon, phosphorus, sulfur, selenium, and iodine. The rest of them are basically liquids and gases. So these non-metallic elements are the only ones that exist in a solid state under normal room temperature conditions: carbon, phosphorus, sulfur, iodine, and selenium. Now there's only one nonmetal which exists in liquid state under normal room temperature conditions, and that is bromine. And pretty much all other nonmetals exist as gases, such as nitrogen and oxygen, fluorine, chlorine, and the elements of group 8: helium, neon, argon, krypton, xenon, and radon. All right? So that's the second category of elements. The third category of elements in this discussion are known as metalloids. And as the name suggests, metalloids, they tend to have properties that are somewhere in between those of metals and non-metals. All right? And these are the metalloids. There are only 7 of them. All right? So these elements, they have some properties in common with metals, but they also have some properties in common with non-metals. All right? And if you look at the periodic table, most legitimate periodic table will look something like this. They would include the group numbers and the atomic numbers. This one does not have the atomic masses, which we'll talk about later on. But the purpose of this table is to show you the different categories that we just discussed. So the ones shaded in blue, those are the metals. The ones shaded in green are the non-metals, and the ones shaded in gray would be the metalloids. And as you can see, the vast majority of elements that we know are metals. All right? And you'll notice that there is a dark line here, which you'll find in most legitimate periodic table, which basically represents the line of demarcation between metals and non-metals. So the metals are basically to the left of that line, the non-metals are to the right of that line, and then we have a few elements that are basically bordering that line: boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. These elements are the metalloids. All right? So that's basically what this indicates. It just basically shows you the different types of elements according to the broad categories of metals, non-metals, and metalloids. Okay, so as stated here, metals are found to the left of the metalloids, and non-metals are found to the right. All right? Okay, we're going to stop here. The next video will deal with the atom, which is the most fundamental particle in an element. All right? So until next time.